6 times I1. Okay? So the drop over here is equal to 6I1. And we keep coming around, and I've got the volts. Plus minus, what happens here? That's a drop. Plus 6. Okay, keep going around. Nothing there. Come around here. This is I3 again, because up here would be I2. This right here would be I2 coming down this way. And see, so I've got I1 and I2 coming in here, but I3 coming out. So that makes sense. All right, so anyway, I1's coming up here, and then I got I3 right here. And what happens here? That's a drop. Plus 2I3. Plus 2 times I3. Okay, just because now all these are all voltages. Okay? Alright, so now I'm going to rewrite this equation. I'm going to rewrite this equation like this. I'm going to say 6I1 plus 0I2 plus 2I3 equals 6.0 volts. How the heck did you do that? Well, what I did was subtracted 6 from both sides. Then I had 6I1 plus 2I3. And then I just put that plus 0I2 in the middle. Yes? What? No sound? No sound. I'm green. I'm hot. What?
Turn it on.
Turn it on?
Yeah.
Turn what on? This thing?
Yeah.
It is. The green light's on. Oh, I don't know about volume. That's beyond me. Oh, there is no volume. They control the volume. It's working? Okay, good. There we go. All right, now. Okay, this one will probably never make channel 17, but that's all right. Got 6I1 plus 0I2 plus 2I3 equals 6 volts. Now, let's look at loop 2. So here's equation 2. Okay? Now, let's look at loop 3. So in equals out. So let's look at loop 2, I mean. Did I say loop 3? That's because I'm loopy. I was up late last night. All right. Making... What? I just pulled it out because I want my equation to look like this guy. I1 plus I2 minus I3 equals 0. And so 6I1 plus 0I2. Because there isn't an I2 there, I can multiply it by 0 and stick it in there, right? Right? So now, there's a method to my madness. You'll see here in a minute what I'm doing. All right, now, let's go through this loop. Let's go through this loop 2 right here. So we're going to start with the gains and drops again. Gains, drops, gains and drops. So, plus 12 volts. And now it's coming up through here and across the top there with I2, that's going to be a drop, right? What was I2's voltage? 9. Okay, good. So it's going to equal the drop will be 9I2. It's going to come on around here, and then it's going to drop. Oh, you can't see. Oh, yeah, you could see that. Kind of. Big, hairy hand there. Anyway, so it's going to go plus to minus. And so, yes, thank you. And it's 2 ohms. 2 times I what? 3. Plus 2I3. Okay? All righty. Now then. Now then. Okay, so now I'm going to rewrite this equation as 0I1 plus 9I2 plus 2I3 equals 12.0 volts. Okay, so there's equation 3. All right, so I'm going to write them all again right here, just because I've got a space right here. So after all that, I'm going to just do now it's time to do some algebra. So I've got I1 plus I2 minus I3 equals 0. And I've got 6I1 plus 0I2 minus 2I plus 2I3 equals 6 volts. And down here I've got 0 I1 plus 9 I2 plus 2 I3 equals 12.0 volts. There we go. Now, basically, I'm going to give you shorthand how you could do this on a TI-83 or 84 real quick. I don't know how to do it on a TI-89. I'm sure it's even easier. But on an 83, you just set up this matrix right here. You'd say, I've got matrix A, which would be a 3 by 3 matrix, would equal 1, 1, negative 1, 6, 0, 2, and 0, 9, 2. And then I'd set up matrix B, which would be a 3 by 1 matrix, which would be 0, 6, 12. Some of you are going, what is he talking about matrices? Don't worry about it. I'm going to show you how to do this. I'm going to show you how to do this here in a second. All right? And then what you do on your calculator is you take a to the minus 1 times b, and that should equal your answer of I1, I2, and I3. That's what we're trying to find. Is we're trying to find what the current is through each one of those things. Then I can find the power dissipated through each one. Okay? All right, so now, how would I do that? Here's how. Well, there's how, but no, here's how. We're going to do it this way. Computer, I feel like Captain Kirk. Computer, give me the calculator for 3 equations and 3 unknowns. Here it is. I'm going to put in my first equation, which was 1, 1, negative 1, 0, right here. I'm going to put in 1, 1, 1, 1. And then again, you guys are going, well, wait a minute. We don't have this on the exam. Right. On the exam, if I give you one of these problems on the exam, we're going to say, just set it up. Walk through it and set it up. You don't have to solve it. All right? But, yeah, we're going to do it today. We're going to get it started. Okay? And actually, your homework problem of this is much easier than this one. This one's hard. This one's kind of killer. All right, and what was the second equation? 6, 0, 2. 6, 0, 2, and it was in 6 volts. And then the last equation was 0, 9, 2, and what? 12. Oh gosh, I hope this works. Please work. Enter. Boom. Yes! The current through I1, and I think your book says this, the current through I1 is 0.5 amps. The current through I2 is 1 amp. And the current through the I3 current is 1.5 amps. Okay? So, we did it. We did it. But the book was asked some interesting questions about it. It said, so I got this. So I know this. I know that on that ugly circuit, I've got I1 equals 0.5 amps. I've got I2 equals 1.0 amps. And I'm probably not even writing where you can see it. No, I'm not. All right. And I3 was equal to 1.5 amps. Now, the book asks, how much power is being dissipated like in the R3 circuit? How much power? Well, what does power equal? I times V. Okay? I times V. And so, or I squared R, actually. So if you want to look at the I2 circuit or the R2 circuit here, how much power is going through there? Power equals IV, where V is equal to I2 times R2. So it's basically power equals I squared times R. That's how much power would be dissipated through that thing. Okay? All right. That's how much energy it's losing. It's sucking up from this guy. But this guy's actually gaining energy. All right? This guy's actually gaining energy through here. All right? So the power dissipating from this guy, the power that this guy is giving up, this 12 volts times 1.5, what's 12 times 1.5? 18 what would it be? IV gives me what? Power is measured in what? Watts. So that'd be 18 watts, okay? It's going through here. However, this guy is getting what? What current is going through? Oh, half. So he's getting 3 watts, but he's gaining 3 watts. So this guy's giving up 18. This guy's gaining 3. Now, all of these dissipated currents here should equal 15. 9 times, this is 9. This one is 1.5 times 2. What's 1.5 times 2? 3. 9 plus 3 is 12. And this one is 6 times a half. That's 3. Came out, worked out right. Okay? So he's pumping out 18 watts. He's gaining 3 watts. So he's hiding 3 watts. So there's 15 watts out there to be dissipated through each of those things. So the power is conserved. Energy is conserved, which is what we want. All right, good. Now, let's go ahead and look at your homework problem. I got that on here. I got that already here. Called up. This guy. Oh my gosh. They're trying to kill us here. Actually, they're not. Let me do this magic trick that I learned. Do that. And you do that. And it all shows up. It should all be there. It's all there. Good. All right. Okay. Now, there's one way. There's a way to do this one that you don't even have to do really what we did. Okay. All right. If we just think about this circuit for a minute. First of all, what's something that I could do to find the amperage that's going through the circuit as it's going like this? What's something I could do to find the amperage? Not here, because what happens here? I've got this amperage that's come along here, then what's it do? It splits. 40% of it goes here and 60% of it goes there. Actually, is what happens. Okay? Exactly. Did y'all hear what Kenna said? She said, hey, can't we just combine the resistors and find what the current is? Sure. You can combine all these resistors and find the overall current that's going through here and here, but right here it's going to split, right? Okay. Yeah, so that's one way to find it. So we could actually find the current that's going through R3, R4, and R5. That's going to be the same thing. Okay? That'll be the same current going through R3, R4, and R5. And let's go ahead and do that. Let's find out what the current is that's going through here. That's going through this wire and then over here to this wire. Now, got a quick question for you. The way the book did it, I looked up how the book did it because I was like, oh, I got my hand waving way of doing this, but that's not probably going to do you much good. I've got, which is what we just did. But Kenneth saw through it, so that was good. But there's actually 2 loops here. The first loop is coming around and then going through this wire right here. Okay? It's coming around and going through this wire right here. And then the second loop is coming around and going down like this. All right? So you can do 2 loops if you want it. But we don't need to do 2 loops because these things are going to split up. In other words, the current will split. This one's a little bit harder. If this was 8 ohms, let's just take this example. If this was 8 ohms and I had 6 amps coming in here, that'd be a lot of amperage. But if I had 6 amps coming in here and this was 8 ohms and this was 4 ohms, how many amps would go through here and then how many amps would go through there, do you think? Yeah, it'd be 2 and 4. Exactly. Exactly. So this one's going to be a little bit different. This one will be because got a quick question for you. Is the voltage the same through here as it is through there? Is the voltage going to be the same? Yeah. Exactly. The voltage will be the same. Okay. All right. Well, let's go ahead and I don't know what it's going to be, but all right, let's go ahead and do that then. let's set up this problem. I'm going to do the first thing. Let's just find the total resistance. Let's just turn this off real quick. .cam. All right, and let's just find the total resistance. Uh-oh. If we find the total resistance here, we've got this. I don't want to make you seasick going back and forth here, but let me just draw this guy. It won't be that hard because we just got this right there. Comes down, there, comes across, dig. And remember, the other thing you can always do is you can just go to that circuit building thing and test your answer. But then again, you're going, we can't do that on the test, though.
You should let us have laptops.
Should let you, but that gets into an equity issue because not everybody, like me, has one. They can use, oh, true. Problem is, the answer is no. Okay.
Would you rather?
What's that?
I've got it printed out. Do you want to just use this?
I'm done now. I'm done now. All right, so here we go. Here it is. Here's your circuit. Isn't that lovely? All right, now here's what we're going to do. Let's find that total resistance again. So these guys are in series, so that's not bad. 2 plus 8 plus 2 is what? 12. And then what are these guys? 1 over 4 plus 1 over 6. No, you don't need a decimal. 1 over 4 plus 1 over 6. What's the common multiple here? 12. So you've got 3 over 12 plus 2 over 12. So you've got 5 over 12. Is that the resistance? No, you got to flip it. 12 over 5 becomes what? 2.4, right? Yeah, so this resistance in parallel here is 2.4 ohms. Okay? And so if I add up all those, RP plus R2 plus R3 plus R5, is that right? What happened to R4? Plus R4 equals 14.4 ohms. Okay? Now, let's take a look at this voltage here. Are these volts, he's pushing charge this way, he's pushing charge that. Are they pushing charge in the same direction? So what's the voltage? Combined voltage of these two guys. Yeah, they're in series. So the voltage is 18. So we've got 18 volts. V equals IR equals I times 14.4. And so when I take 18 and divide it by 14.4, I get 1.25 amps. So I equals 1.25 amps. Now, where is that I? That's the I that's going through here. I thought I saw a hand up. I guess not. It's the I that's going through here. It's the I that's going through here. Is that it? Why do I keep thinking, how many resistors? 1, 2, 3, 4, 5. Okay. All right. Whoa. All right. So now. Okay. So there we go. Now then, we've got now we've got the junction rule here. We've got the junction rule here. We've got a problem here. We've got a problem here. We've got I1, we'll call this I1 and I2. I1 plus I2 equals I, which is 1.25. Okay. Now, I did some kind of screwing. It actually worked out pretty good. What I did was, well, first of all, what's the voltage going to be through there? What's the potential drop there? What's the total voltage in our thing? 18. They're in parallel. So what's the voltage? 18. So we can figure out the I, right? I think we can. Oh, no, that's going to be huge. Wrong. That is so wrong, what I was doing. That is so wrong. Yeah, because we got to include all these drops. That'd be a gain, and then we got another drop there. So it's actually losing steam here. We could figure out what all these drops are and then go in there. But here's an easier way to do this. Here's an easier way to do this. Notice, this is 4, this is 6. Okay? So, yeah, take 40% of one, take 60% of the other, and boom, you've got it. 40% of 1.25 comes out to be 0.5, and 60% of the other one comes out to be 0.75. And you've got it. So I1 and I2 is 0.75 because I1 equals 40% of I, and I2 equals 60% of I. So we didn't have to do all that looping around. We just had to do the one big loop. Goodness gracious. All right. This is just a real simple circuit. The other circuits for computers are semiconductors, and it's even harder because the current only goes one direction and it can't flow back and stuff like that. So.
Then the second part of it, where you calculate the P, you just use the I or the I squared.
Okay, and Rashida said, hey, to find the power in each one of these, to find the power that's dissipated through here, you can either, it's P equals I squared times R. Right, yeah, they give you the R.
Yeah, they give us they give you, they might ask you one for like either R2 or
Right,
6.0 or 8.0.
Right, yeah.
Which,
Yes, Rick. So,
Isn't the current inversely proportional to the resistance? Shouldn't there be more current going through the resistor that's smaller?
absolutely. What he said. Flip those around. So I2 is equal to 60% and I1 is equal to 40. There we go. Very good. Yes, Sarah.
What if your resistors on that loop didn't add up to a multiple of 10? Like, what if it was like 8 plus 7?
8
It
and
was like
7.
15.
Yeah, then it'd be out of 15. They go 8 over 15 times 7 over 15.
Oh, okay.
It'll work out. Be a
Can you
nice
reverse
proportion.
it?
What's that?
Why do you have to make an inverse? I don't understand. Why did it go from 60 to 40?
Oh, because of Rick's insight here. He said, hey, wait a minute. If there's less resistance, is the less resistance going to get more current or less?
Oh, okay.
It's going to get more. It's going to get more. Very good. Thank you. Good. Conservation of charge and just the way energy works. Okay? All right. Let's talk about, real quick, and then we'll do one other problem, too, because I've already looked at it. Let's talk about this. I'm going to show it to you first. Let's go to the computer. Here you go. I've already built it. Basically, what we have is an RC circuit. I've got a resistor, and I got a capacitor. All right? So right now, nothing is charged because I don't have my battery in there yet. But when I put my battery in there, what's going to happen? I'm going to get everything in place here. I'm going to put my battery in here. Notice there's nothing flowing because there's nobody pushing charge. I'm going to put this guy here. There should be no voltage because there's nothing stored there. I'm going to get another voltmeter. Can I get another? Oh, I thought I could get multiple voltmeters. Nope, can't do it. All right. So anyway, well, eventually, I'll just leave it there. I'll just leave it there. And let's go ahead and put the battery in. Let's go ahead and put the battery in. Let's split the junction here. Oh, please don't do that. Okay, there we go. Now then, basically what I'm going to do is close the switch. I probably should have just put the switch in there. That would have been easier. All right, I'm going to put the switch down here. And what's going to happen is you're going to see it ramp up or amp up. Okay, it's going to amp up. And I'm going to get a bunch of charge collecting over here. Right? Going to get a bunch of charge collecting. And then eventually, what's it going to do? It's going to, all these electrons are going to build up over here. And they're going to stop the flow of electricity. All right? They're going to eventually stop the flow. All right? And that takes time. That takes time. So when we're building up, so I'm going to give, the first equation I'm going to give you is when we're building up the charge. And then the second equation I'm going to give you is when we dissipate the charge. So here we go. Let's just take a look at what happens. And it'll take time for this to happen. Now watch the amps. And watch the voltage across the voltmeter. Okay, there we go. The voltage across this thing is dropping. It's dropping, 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 dropping. Across that resistor, dropping, dropping to 0. And now my amps have completely stopped. Now this guy's completely charged. What was my starting voltage? 9? Was that it? I can't remember. Was it 9? What do you think the potential difference is now between these negatives, or these positive and these negative charges? What do you think it is? What's the voltage difference? The potential, the voltage. 9. Should be 9. Let's check it. Doink. Yep, it is. Okay, so it's 9 volts, just like it was between the battery. All right, so now that thing is completely charged, and so one thing we can do, we can unhook it. So this is like your cell phone or whatever. So we're going to remove the battery. And so it's on a different, so we unplug the diode. Actually, there's a little diode that changes the AC current to DC current that charges your cell phone. And then we hook this together. And you make a call. Boom, you're calling, texting, calling, texting. Uh-oh, called and texted too much. Now you're out of power again. So now you got to do it again. Now you got to ramp it up again. Okay? Now, one of the nice things that we're going to learn about when we get to AC circuits, let's put this battery in here one more time. But this time, I'm going to put this guy in here just to kind of whet your appetite for it. This guy's called an inductor. And because of the magnetic field that he has, okay, it's going to charge that up. Because he's got this coil here, and let's get that down to, oh, he's starting to make it go back the other way now. Is it still charged? No, it's going less and less. Keep going down. Okay, remove. All right, now, nothing's moving, but when you put an inductor in here, something kind of cool happens, actually. It flows, and it also controls the flow, but then it comes back. Starts building up the other way. And it flows back. You think this could go on forever? Not really. It could go on for a little while. It's kind of a cool little thing, but it's not a perpetual motion machine because this is an idealized situation, there is resistance in the wire. I mean, there's actually, that's taking energy away. Okay, that'll eventually stop this little thing. In fact, this is kind of real. All right, so that's the idea behind what we're going to do now, which is look at the, not at anti-lock brakes. I don't even know why I'm on that page. But anyway, sorry. Because I want to do one problem. For you. Yeah, we got a little time. Okay, RC circuits. All right, here's the equation for when you're charging up something. Here's the equation for when you're charging something. Okay, you got this. You have the voltage across the capacitor. As we showed, it's going to build up equals V naught, which is the voltage in the battery, which is your original voltage in the battery, times 1 minus e to the minus t, the time that it's running, over RC, where R, oh yeah, this is going to be your quiz. I forgot. This looks scary for the quiz. Okay? This is, RC is called your time constant, which is ohms, RC. And guess what? That's in seconds. Here's your quiz. I want you to talk among yourselves. And so get a separate sheet of paper or have one person be the poor schmuck who's got to give paper to everybody. All right? I want you to show me why RC is seconds. You haven't taken physics class until you've shown that RC equals seconds, okay? It's kind of like you haven't done physics until, I don't know, other things too. You've done E equals MC squared, which we'll get to in April. Okay, so why would RC be seconds? R is resistance. Think about what resistance is. Think of Ohm's law. Think of Ohm's law, where V equals IR. And think of what capacitance is, where capacitance equals, where Q equals C times V. There's your hint. Okay? And also think about what I is. What is I? It's amps, but what is it? See if you can figure that out. This is, take about another couple minutes. Do. Did y'all get it? Hold on. Don't forget to put your name at the top of this thing. And see what happens, because RC is in seconds, that seconds over seconds, that cancels, and so you just have a number. And so you get the voltage equals a percentage. Okay? It's an ugly little equation, but it's because it's a dissipation. It looks like this. When things dissipate, it looks like that. Anytime you got something that looks like that, use e to the minus. Use it in statistics all the time. All right. Did we get it? No. No. Not even going to play with it. Nope. All right. Try this. Put V over I equals R and stick that here. And so you get V over I. And then what does C equal in terms of Q and V? Q over V. What cancels right away? The V's. Now I'm left with Q over I. Well, does that get me anywhere? What does I equal? Q over S, right? So I equals Q over S. So I got this. Since I equals Q over S, I've got Q over 1 over Q over S, which equals Q over 1 times S over Q. Ta-da. There you go. So it equals seconds. So what we wind up with, even though we've got all this resistance, we've got all this capacitance, we've got seconds over here, basically we wind up with a voltage equals voltage because it all cancels out. All right? So the math makes sense. Let's just see what a problem looks like when we do this. Let's read a problem and do it. All right. In fact, let's do your problem. Since you're here, since you all came and you were good sports and took my little quiz, which I'm going to collect here in a minute. All right. Let's take a look at this homework problem right here, because I've already looked at it. Mastering physics, previous. Oh, that one's kind of a nice little. That one's not bad. That's just putting. Oh, we're going to do the galvanometers on Monday. All right. So now we've got. Here we go. It says a capacitor in a single loop RC circuit is charged to 63% of its final charge in 1.7 seconds. Okay? So it's saying this. It's saying VC over V naught equals 0.63. Whoops. What that's saying is this. VC over V naught equals 0.63. Okay? Equals 0.63. And the time that it took was 1.7 seconds. They want to know what the time constant is, what RC is. Okay? The example in your book says, hey, what is the, now remember your seconds might change to protect the innocent here, but anyway, yours might be 1.9, this might be 65, whatever. Okay, so anyway, the example in the book was a little bit trickier because it said it gave the capacitance, but then it wanted us to find the resistance. So that was a little bit trickier. This one's kind of nice and straightforward because we know this. We know that VC equals V naught times 1 minus E to the negative T over RC. Or, well, where RC is that T naught. Now then, when this is equal to 0, what does this equal? 1. So you get 1 minus 1. So V naught times 1 minus 1, when T equals 0, what's our constant? What's our voltage? 0, which makes sense. Before it starts going, it's at 0. And then as it builds up, all right, so now we've got a tricky problem here. So we got VC over V naught, so we got 0.63 basically equals 1 minus E T to the RC, which is equal to tau. I keep forgetting to put the tau down there. How do we do these problems? Y'all remember? Ferg's going, no idea. All right, let's do it this way. Let's subtract 0.63 from both sides and add e to the minus t over RC to both sides. So I wind up with e to the minus t over RC equals 0.37. So I've got a nice positive number here. Okay? Okay. All right. So now, let's do this. Here's what you do. Let's just take the reciprocal of this. Because really, this is saying this. This is saying I've got 1 over e to the t RC. In case you forgot some of your algebra there, remember the negative exponent means it's just down here, equals 0.37. So let's just flip it over and say e to the t RC equals 100 over 37. Now what do we do? There you go. Natural log. Yep. What? No.
That's why you have to do this.
Right. Well, it actually, if you take the natural log of this, it does come out to be negative TRC. Yeah, right. Okay, so now you just take the natural log of both sides equals the natural log of 100 minus the natural log of 37. I think that's the way logarithms work. It's been a long time. What's that? Oh yeah, when I get done, yeah, but when I do that, when I take this function, because the natural log is the inverse function of this guy, so I wind up with t over RC equals whatever this is, natural log of 100 minus the natural log of 37. You could have also just done the natural, on your calculator, taken the natural log 100 divided by 37 and gotten that. All right, and then you multiply by RC on both sides and divide. Boom. Because they gave you t equals 1.7 seconds. There you go. Oh my, don't forget to turn in that whopping quiz that you turned in. We are done, basically, with chapter 4, or chapter 18.